Greetings, grade 10s. How are you guys doing? Welcome to our first physics lesson for grade 10 physics. This is your teacher, Marshall A.C. Candiado, and I hope you guys are well. And today we want to look at the topic effects of forces. We want to look at the effects of forces, specifically looking at Hooke's law. I know you guys had done on the work that I sent you earlier on the WhatsApp groups. You had also looked at questions on Hooke's law, but I'm just going to take this opportunity to explain, so that it's almost as if we are now discussing, and I'm hoping you guys have read about Hooke's law, and now I can come in and maybe explain some points or some areas where you were not really understanding. So when we are now looking at these effects of forces, I was looking at your living physics, where we were supposed also to look at forces in everyday life. But you realize that the concept of forces in everyday life is a concept that we covered in grade 8, we covered it in grade 9, and even in the next lesson, I will touch on some of the effects of forces in how forces have different effects on different objects, right, and on different objects in terms of acceleration and in terms of shape and size. But for today, we will want to look mainly at Hooke's law. Okay, so what are the objectives of today's lesson? By the end of the lesson, you should be able to state Hooke's law, and recall and use the expression F is equals to kx, that expression that is there. So you should also be able to plot and interpret extension load graphs. So there will be examples, right? There will be examples that will show, and I'll give you a table which will have some information in it, and you guys will then draw the graphs. You draw the graphs, and then you will send me the graphs you would have drawn on our physics group. Okay, you will send me the graphs on our WhatsApp physics group. So you should also be able to use proportionality in simple experiments. Use proportionality. You should be able to identify, if you remember, we talked about direct proportion and indirect proportion. Direct proportion and indirect proportion. So before we jump into Hooke's law proper, right, we just want to know that force, the unit for force, is given there. We normally measure force using the unit of newtons, right? Newtons. Then we describe forces in terms of their ability to change the size, the shape, the motion of an object. These things are basic. If an object is moving, if a vehicle is moving and you are driving, you're in a car and you're moving from here to Oshakati, or we are moving from here to Ongwediva, and you step on the accelerator and then the car starts moving faster, that is a force that has actually propelled the car, and then it causes the car to move faster, right? So that is an example of a force. If you were playing soccer, you are there very much, and you guys are playing soccer with Devin, and then you kick the ball in one direction, he stops it, he kicks it again in another direction. That's an effect of a force, right? So, or if you want me to say it's you, Elinatse, and you're playing, I don't know, with Maria or with whoever it is you're playing with, you guys are always throwing objects, you're always moving objects, whether it's plates. That's forces just acting there. Those are just different examples of forces acting basically in everyday life, right? So we will look at, here we just included Newton's second law of motion. We will look at Newton's first law of motion, and then we'll also look at Newton's second law of motion. but this one is saying that it basically says that the force of an object is proportional to its acceleration, right? And then it's about the effect which the force has on an object. So if you push an object and you push it very hard, then it's going obviously to move faster, right? It's going to move faster. So there's a direct proportionality. We wouldn't expect you to push an object with a lot of force to the you are there, you're pushing an object. You push a table with a lot of force, right? And then the table moves only a small distance. Then someone comes and pushes the same table on the same floor, but then it moves a great distance. That would not necessarily make sense. So there is an element of proportionality. So that's what proportion means. To say if you do something, the effort that you put in is usually directly proportional to the result that you get. Okay, so now let's look at Hooke's law. What does Hooke's law state, right? So we have Hooke's law here saying effectively the stretch or extension of a spring is directly proportional to the force applied on it, provided the limit of proportionality is not exceeded. So my part in this, because I know you guys can read, you can read all of those things by yourself. My part is to come in and explain on this concept of limit of proportionality not being exceeded, right? So what do we mean when we say limit of proportionality not being exceeded? So if you were to have an elastic band, right? Let's think of an elastic band. You guys have elastic bands. If you were to pull that elastic band, right, usually a rubber band, we call it an elastic band, we call them rubber bands. You can think of a spring, you can think of shocks on cars. The extension with which that spring extends or stretches out is directly proportional to the force which is applied, right? Is directly proportional to the applied force. But then we'll look at how when the limit of proportionality, that's to say the extent to which you can stretch that rubber band. So if you are stretching the rubber band and then you pull it too hard, right, it's obviously going to break, right? It's obviously going to break. Or if it's a spring, if you've ever seen a spring, then the spring is going to slacken. The spring is going to slacken. This is an example of a spring, right? So we're going to use this one. I'll be using these diagrams in this lesson to explain the spring constant. But this is basically a spring. If we're looking at this one, this is basically a spring. So this is a load. So you would have a spring, and then a load can be placed on it. This is a spring. This is the load. So if the load is placed on this string, and then you observe here that the spring is stretching, right? The spring is stretching. No, that's me just enlarging the size of the video, right? The size of the image, right? So if it expands, right, or if it stretches out, and then the way it stretches out is in proportion to the mass or the weight or the force that is being applied on that spring. So you can observe here that this one is not as stretched as this one, right? Because the weight, you can see the blocks that are being placed here, they are different. These ones are less, these ones are more. So you can tell you that, okay, so if you've ever seen, right, so you guys should also take this chance to write down the word Newton meter or a force meter, right? Write it down. Please write it down somewhere. Write down the word force meter. Okay. So now if you've written the word force meter, you can pause the video and you can look for a force meter, right? On the internet, you guys are online. You can look for a force meter on the internet, right? So, and then you will see how it measures the weight of an object. And that force meter has a spring inside of it. If that spring, if its limit of extension is exceeded, it will effectively slacken. It won't be able to go back to its original position, right? The thing with the spring is that if you stretch it out, it's able to go back to its original position, right? So let's look here, right? So what are we talking about? Then, if we were going to plot the graph, right? If we were going to plot a graph for an extension load graph, right? If we were to plot it, you would find that it would look like this. This is what it would look like, right? It would look like this. You would have it having almost a straight line, because it's directly proportional. As you increase the load, right? As you increase the load, the extension also increases. So as you increase the load, the extension also increases. So it's directly proportional. You won't have a situation where you are increasing the load, but then the extension is actually decreasing. That doesn't happen with Hooke's law, right? It doesn't apply. And I'm sure we've seen springs, we've seen elastic bands, and we know how they work. Right? So the extension is directly proportional to the load that is being applied on it. However, on this graph here, we observe where it starts to curve, because it's a straight line. If you follow it, it's a straight line everywhere I'm touching there. But here at the end, it begins to curve. The line begins to curve. Why is it curving? When it starts curving, it shows that the moment it curves, it shows you that the limit of proportionality has been exceeded, right? The limit of extension has been exceeded. So that is the limit of proportionality. If the line is a straight line and is going up nicely, then the limit of proportionality has not been exceeded. And if you were to remove the load on the spring, it would go back into its original position. But now, if the moment the line curves and you now have a cave, it tells you that you have damaged the spring and it will not go back into its original position, right? So for now, you guys can pause the video a bit, right? You can pause the right. I hope you guys were able to just pause the video that was just to take a break. I also just needed to take a break, just to take a breather, okay, so that we can just look at the material that we are discussing. So we can just look at the material we're discussing, and you go back, you read, and you understand what is going on. Right. So let's look at determining the spring constant. It's an important part of this lesson. I want us to be able to determine the spring constant. So we have the formula for calculating Hooke's law, right? The formula for calculating Hooke's law, is this one. Force is equal to a constant K multiplied by the extension. So that's F is equal to Kx. F is equal to Kx, right? Where F represents the force, K, the letter K, represents a constant, and that constant is applicable and is specific for each and every spring. Each and every different elastic object that you use has its own elastic or spring constant, right? So if it's a spring, it has its own spring constant, which is K, and sometimes we are asked to determine that spring constant. So in this lesson, I'm going to show you guys how we can, if we are given the load, the weight of the object that was on the spring, and we are given the displacement or the extent to which the spring stretches, it's possible then for us to calculate the spring constant, right? So let's look at an example here. So what happens here is that we are shown a spring. This is the spring, right? And these are weights. These little blue things that you're seeing here, they are weights, and they're going to be placed on the spring. This is just a ruler, and it shows you it's what is the one that's going to be measuring the displacement. So when we place a weight here, this weight will, the mass or the weight will be given. So it will be a mass of 50 grams or a mass of 100 grams. But because we are talking about force, let's pay attention to this particular point. Because we're talking about force, if you are given a mass and they say the mass is 50 grams, you should then be able to change that mass into weight. You should recall the formula. How do you change mass into weight? I'll just give you the baseline where we know that 1 kilogram is usually equivalent to 10 newtons. Right. So now moving on. So what you see here, right, is that here the mass is being measured in grams, and then the displacement is being measured in centimeters. But if you remember, force, the unit for force is the Newton, right? It's the Newton, and then when we want to talk about this spring constant, it's in newtons per meter. It is in newtons per meter. So we should be able to convert our mass, because here you'll find that each of the blue weights that we're going to be placing on this spring has a mass of 50 grams. Each of the blue weights has a mass of 50 grams, right? And the spring and the ruler, right, here is graduated in centimeters. Okay, so we will have a situation where they took 4 different recordings. We have 4 different recordings that we have carried out. We place a 50 gram mass on the spring and the displacement. Let's take a chance to look at these 4 diagrams. These are the 4 sections of the diagram. Okay, so take time, right? You guys can effectively rewind and go forward and look at these diagrams. Right, so we are now able to observe, we've been able to observe from the 4 diagrams that we have here, that when the mass was 50, the displacement was 2 centimeters. When the mass was increased to 100 grams, the displacement then increased to 4 centimeters, 100 grams, 4 centimeter displacement, 150 grams, 6 centimeter displacement, 200 grams, 8 centimeter displacement. If we recall from the law, right, from what we are told about Hooke's law here, see that if you double the load, the spring stretch will also double. If you triple the load, the spring stretch or extension will also triple, right? So this is true for any spring whose elastic limit has not been exceeded, right? So it holds true. It's a law. That's why it's called Hooke's law, right? It's not a theory. It's not a story. It's a law, right? So now, having gotten that information, it's then placed into a table, right? So this is also important. Remember, the first topic is where we spent so much time talking about how you should be able to draw tables and place information into them accurately. So now when you have placed your information in this table, right? You have placed your information. First, you place the information in the table, and from this table, you should be able to draw. A graph showing extension, right? Extension, load versus extension. The load is going to be on the dependent variable, while the extension is going to be on the independent variable, even though the extension is dependent on the load, right? So please, I will need you guys to draw the graph for this table. Let us refer to it, we'll call it table 1. So you guys will draw the graph for this table, right? So now, I also want us to look at the calculation. There's a calculation that I want us to look at calculating spring constant. Right, how to calculate spring constant. So I just took effectively that information that was on that same web page and I brought it here, okay, because I wanted to do a calculation where I could explain to you or just give you an example and do the calculation for you. So we know that the formula, this is the formula F, force is equals to constant multiplied the spring constant, right? F is equals to Kx. Okay, so now if we are given the x is standing for the displacement, we are given the displacement already given. So F being the force, we are given the force, but the force now is in the form of mass. So we have to change the mass to weight, because weight is a force, but mass is not. Weight is a force, mass is not a force. So we have to change this weight to a force. So this the mass into a force. So I gave you this example. We said 1 kilogram is equivalent to 10 newtons. Therefore, 100 grams would be equal to less. Remember those calculations for proportionality. 100 grams would be less. So 100 grams is actually equivalent to 1 newton. 1 newton only. So displacement should be in meters. Displacement should be in meters. So you should convert the centimeters that are there into meters. 4 centimeters, changing it to meters is equivalent to 0. If you want to change centimeters to meters, you know you divide by 100, because you have 100 centimeters in every meter. So you say that your answer you get as 0.04 meters, right? So your K, because here you have already done what we call the subject of the formula, because you want to find K, it means that you have to divide both sides by x so that the K can then remain on its own. So K becomes K is equals to F, that's the force, divided by x, which is the displacement. Okay, right. So having done that, I'm getting a bit lost, right? So here, our K, our constant, is equivalent now to that mass, which is 1, that weight, which is 1 newton, divided by 0.04 meters, which is equal to 25 newtons per meter. That is the spring constant for that spring, right? Therefore, spring constant K is equal to 25 newtons per meter, right? So you guys, like I said, you're going to draw the graph for this table, right? You're going to draw the line graph for this table. You are also going to draw the line graph for this table as well, and you are going to calculate the spring constant K for this second spring. This is a different spring, right? This is a different spring. So you guys are going to calculate the spring constant for this spring, and you're just going to draw a small, it's a very simple line graph from this information that you have been given. But I want the information to show the load and the extension. The displacement is the extension, right? The mass is the load. Okay, so at this point, I will need you guys. I'm basically trying to explain. I've tried to explain as fast as I could, and still leave you guys with enough material to also be able to explore for yourself. So that is the homework that you guys will do. This is the first lesson. In the second lesson, we'll look again at force, and we'll look at some of the effects of force, and we'll do a lot of calculations on force. F equal to ma, mass times acceleration. So we'll do several calculations on that, right? So I hope you guys will stay well. Have a great day. Thank you.